Hello, welcome back. Lesson 4, Unit 4 of Algebra 2. This lesson we're going to learn how we can solve a system of equations by using the matrix equations and the matrix equation solving techniques that we discussed in Lesson 3. So consider this system of equations I have here. I'd like to demonstrate that this is in fact equivalent to a matrix equation. So what we're going to do is we're going to form a matrix equation and then we'll check it to confirm that that's the case. So here's the equation that we would be using. The equivalent matrix equation is 2, -1, 1, 1. And I get those numbers from the coefficients of that matrix. Excuse me, of the coefficients of the variables. Then I'm going to make a 2 by 1 variable matrix, x, y. And then I'll put the constants over here in a single 2 by 1 matrix. So it's my claim that this matrix is exactly the same thing. Well, let's talk about what this is saying. This is saying that 2x minus y is equal to 8 and x plus y is equal to 1. So what I'd like to do is I'd like to multiply these two matrices together. This is a 2 by 2 times a 2 by 1. So they definitely can be multiplied, and the result, this is a 2 by 2 and this is a 2 by 1. So the result will be a 2 by 1. Remember, we multiply rows with the columns. So 2x, 2 times x, then plus -1 times y would be just a minus y. And then over here I have a 1x, that's just an x, plus a 1y, so that's just plus y. And we know we're saying that those two multiply together to 8, 1. So what does that mean? Well, that means if two matrices are equal, means that each of their corresponding elements must be equal. So this element, that 2x minus y, is one element. It's element in row 1, column 1, must be equal to row 1, column 1 of the equivalent matrix. And, you know what? I wrote x plus x here. That should be an x plus y. Let me fix that real quick. Okay, and like I said, the elements have to be exactly the same. So this second element, the element in row 2, column 1, must equal row 2, column 1 of the other. So you can see you may not have understood how I created this matrix equation from this, but you can see that it certainly is equivalent when we do matrix multiplication and then just apply the definition of equivalent matrices. So this equation here must be the same. Again, I took the coefficients from the matrix and made that, from the system, made that one matrix. Then I made the variables x, y, and they have to be in that order, x, then y, and then equals 8, 1. In order to do this, you got to make sure your variables are set up like that, x, then y. All right, well, what we're going to do now is we're going to solve this equation that we created in the first example. And we learned in the last lesson how to do that. The way we do that is we first find the inverse of this matrix, and then since this matrix is on the left, we will multiply on the left with it. Okay, so the inverse of this matrix, I need to find the determinant. The determinant is 2 minus a -1, so 3. All right, and then the inverse, you flip-flop these 2 points, these two values, and change the signs on these two. And that whole thing has to be multiplied by 1 over the determinant. So my inverse must be 1/3, 1/3, -1/3, 2/3. And I'm going to multiply that by 2, -1, 1, 1 times xy equals 1/3, 1/3, -1/3, 2/3, and we multiply on the left. Notice this wouldn't actually even work if I multiplied on the other side. It would not, the dimensions wouldn't match. This is a 2 by 2, this is a 2 by 1, so it works. Okay, so 1/3 times 2 is 2/3. 1/3 times 1 is 1/3. 2/3 plus 1/3 is 1. That's a -1/3 plus 1/3 is 0. -2/3 plus 2/3 is 0. positive 1/3 plus 2/3 is 1. So that's our identity matrix. And this becomes 8/3 plus 1/3 is 9/3, which is 3. Then negative 8/3 plus 2/3 is a negative 6/3, which is 2. And we know that the identity 1001 times xy should be xy, but let's check. 1 times x is x. 0 plus y is just 0. Then 0 plus x is 0, plus 1 plus y is y. So that did indeed work out. And so what is this telling me? Well, remember that equivalent matrices have to have equivalent corresponding elements, so x must equal 3 and y must equal 2. And you can check, but that certainly is true. You plug it in, you would get 6 minus 2. Excuse me, what I've got something not right. Oh, yeah, I was about to say. I said it would check, and then it didn't. There we go. That's a negative 2 there, isn't it? So 6 minus a negative 2 is 8, and then 3 minus 2 is 1, so it works. All right, what I'd like you to do is to pause the video, set up a matrix equation, and use inverse matrices to solve. All right, let's see how you did. The equation is 3, 2, 2, 1, the coefficients, then x, y, and the constants are 7, 4. And you can check to make sure that works. I'm going to just go over here and do some of what I call my inverse work. So the determinant is 3 minus 4 is negative 1. And then we know that we switch the values in this diagonal and change the signs on the value of this one. But then I have to multiply by 1 over the determinant. So that becomes a negative 1, 2, 2, negative 3. So that's my inverse right there. And I will multiply on both sides by it. And I think it is always a good idea to double check that your inverse really does give you the identity matrix, because it's easy to make a mistake when finding an inverse. But you'll know that if it gives you the identity, that's the one and only inverse that has to be correct. This is on the left, so we have to multiply by our inverse on the left. Remember that, very important. So this has to go on the left-hand side. And it, in fact, would actually not work. It would be undefined if I put this on the other side. All right, negative 3 plus 4 is 1. Negative 2 plus 2 is 0. Remember, rows with columns. 6 minus 6 is 0. 4 minus 3 is 1. Very good. We got it. All right, negative 7 plus 8 is 1. 14 minus 12 is 2. So that is telling me 1 times x is x plus 0y. That must just be an x. 0x plus 1y. That just equals a y when you multiply. So we know that x equals 1 and y equals 2. Now, if the coefficient matrix for a system of equations is singular, remember that means that the determinant is 0, then the system will not have a unique solution. It could be infinitely many, it could be no solutions. We would have to do a little bit more work to figure out which, though. So let's talk about y. Let's take a look at this system of equations here. The coefficient matrix would be 6, negative 8, negative 3, 4, and then xy equals 10 and 2. So let's find the inverse of this matrix. We need the inverse. So first I need the determinant. That's 24 minus, and then negative 3 times negative 8 is also 24, so it's 0. Then we know we flip these two positions and change these two positions sign. But I have to multiply by 1 over the determinant. But 1 divided by 0 is not allowed. That's undefined. So this has no inverse. So we can't cancel this out. So this doesn't work. We can't figure out numbers here that make this true. So we're just going to have to say that it's not independent. Or another way of saying that is no unique solution. Could be that it has no solution. Could be it has infinitely many. So in other words, it could be that it is inconsistent system, or it could be that it's a dependent system. So But the technique for doing that with the matrix is something I want to wait and do in a later lesson. So we're just going to stop right there on that one. But I did want to go over that. All right, I want you to solve the following systems of equations. If no unique solution exists, state so. I'm not saying both of them will, but there's two of them here. Please do that. Okay, let's go over and see how you did. 1, -2, 4, -1, x, y equals 4, 9. I'm going to get my inverse by getting first the determinant. That's a -1 minus a -8. So this -1 plus 8 is 7. And then I will flip the position of those two numbers and change the sign of these two. But I have to multiply by 1 over the determinant. Now I'm going to show you a little trick. 1/7 is kind of an ugly fraction. Why don't we wait and just leave that there? Okay? We can do that. We don't have to multiply by the 1/7 now. We can multiply it by it at any time. Scalar multiplication can be done before or after the matrix multiplication. And that's kind of a little trick that I was hoping you would catch on to. That's not a 9. That's a 4, right? That's supposed to be a 4. My pen kind of bled over, didn't it? And then this is a positive 1. Oh, still in my 1/7 over here, though. So let's take a look. This would be a -1 times a 1, which is -1, plus 8. So that's going to be 7. -1 plus 8 is 7. Then this is a 2 minus 2 is 0. This is a -4 plus 4 is 0. This is a 8 minus 1 is 7. Which doesn't look like the identity, but it is if you scalar multiply by 1/7. So that's good. And then this becomes 1 over 7 times. This is a -4 plus, remember this is a 9 here, plus 18, so that's 14. That's a -16 plus 9, which is a -16 plus 9 is a -7. And then when we kind of simplify this all out, 1/7 times 14 is 2, and then that's -1. So let's check. 2 plus 2 is 4. 4 times 2 is 8, plus 1 is 9. So it works. All right, let's do the next one. So we have this coefficient matrix, 1, 3, 2, 6, times xy is equal to the matrix 9, 18. Okay, let's get the inverse. We have 6 minus 6. Oops, that's 0. We know the inverse is multiplied by 1 over the determinant. So my determinant is 0, so this solution must not have a unique solution. Either inconsistent or dependent. Not sure which one. We could find out, though, but we'll just leave it at that. All right, for now, I want you to go ahead and do a couple practice problems here. I want you to find A plus B using these matrices, A times B. That is the symbol for A inverse. The determinant of B and the determinant of C. I just kind of copied C down there again for me. And then I want you to find B squared. So it's B times B. All right, let's do pause the video and give it a try. All right, let's see how we did. So A plus B. Remember, when you add, the rules are a little different than multiplication. You have to have the dimensions exactly the same, and you just add the corresponding elements. So this would be 3, -1, 1, 8. Now we'll do A times B. So in order to multiply two matrices together, we have to have the columns of the matrix on the left have to equal the rows of the matrix on the right. So this is a 2 by 2. This is a 2 by 2. Because those numbers match, we know this is good. And the outside numbers tell you the dimensions will be a 2 by 2 as well. So 2 times 1 is 2. Negative 3 times 2 is negative 6. Then I have 4 minus 12. Then I have a negative 1 plus 8. Then a negative 2 plus 16. And again, if that's confusing to you, please go back to the other lesson and prior lesson and lesson 2 and review that. But you're multiplying each row with each column and you pair them up. 2 with 1, negative 3 with 2. So if I simplify that, I get negative 4, negative 8, 7, and 14. All right, let's take a look at A inverse. So A inverse, 2, A is 2, negative 3, negative 1, 4. So to find the inverse, I need the determinant. So that would be 8 minus 3, which is 5. So my determinant is 1/5. So now what we do is we flip these two numbers positions. So that's a 4 goes there, 2 goes there. And then we change these two numbers' signs, the ones in those diagonals. So we got 4, 3, 1, 2. We're going to multiply by 1 over the determinant. So 4/5, 3/5, 1/5, 2/5. All right. That is asking for the determinant of B, 1, 2, 2, 4. So 1, 2, 2, 4. Define the vertical lines being determinant. So multiply there and subtract and multiply there. 0. So it's a singular matrix. Let's practice finding the determinant of C. Do you remember how to do that? Rewrite the first two columns is my trick. And then you do diagonal like this. 1, negative 3, 4. So that's a negative 12. 2, negative 3, negative 1, 3. That would be a negative 6. So we're going to add negative 6. Then 0 times anything is 0. So we're adding 0. So we've done the three diagonals. Here, here, here. Now we got to do these three diagonals going up. So those are all minus. So 3 times a negative 3 is a negative 9. And 1 times a negative 1 is a negative 1. 4 times 2 is 8. Times 2 is 16. So minus 16. So what is it? Negative 18 plus 9 is, what is that? Negative 9. Plus 1 minus 16 is negative 24. Hopefully I did my arithmetic there. If I didn't, well, you can fix it. Tell me in the comments. All right, 1, 2, 2, 4. That's what we're going to multiply times itself. 1, 2, 2, 4. So that's how you square. So 1 times 1 plus 2 times 2. So 1 plus 4 is 5. 1 times 2 plus 2 times 4. That's 2 plus 8 is 10. Then this row in this column, 2 times 1 is 2 plus 8 is 10. This row, this column, 4 plus 16 is 20. All right. Last thing I want you to do is to practice solving this equation, matrix equation. It's not a system of equations because this is actually a 2 by 2 that we're missing. But go ahead and give it a try. Okay, so what I'm going to do is I'm going to simply cancel this matrix by using the additive inverse, which is just subtracting this matrix, which is basically just changing all those signs. So negative 4, negative 3, negative 1, 5. Remember the additive inverse, it's just the opposite numbers. And when we add matrices, you just add them part by part. So that makes 0, that makes 0, that makes 0, that makes 0. And 0, 0, 0, 0 plus anything doesn't change the matrix. So that's gone on the left. And then on the right, we have 2, negative 4, 2, 4. And now what I need to do is get my inverse. So the determinant is 8 minus 6 is 2. So our inverse will be flip these two numbers. So this becomes a 4 and that 2. But I got to divide by my determinant. So 2 and 1. Change the signs on these two numbers, but divide by the determinant. And I know I did that kind of in two steps, in two things in one, but hopefully you followed. And we are x is on the right, so we are multiplying on the left. Very important that we do that, or we will get the wrong answer. 2, -4, 2, and 4. All right, that's going to be, let's see here, 4 minus 3 is 1, 6 minus 6 is 0, -2 plus 2 is 0, -3 plus 4 is 1. So that's going to be our identity, so I'll just call that x. Then that's 4 minus 3 is 1. -8 minus 6 is 2. -2 plus 2 is 0. 4 plus 4 is 8. And there we have it. So that's the end of lesson 4. You need to practice, of course, and I'll see you in the next lesson.